Hello students, in this module we are going to check the Kaplan Meier estimations 2 using R, the importance of Kaplan Meier estimations, the application part and the statistical inference will be drawn from a sample data using R. Kaplan Meier survival curves is defined as the probability of surviving in a given length of time while considering time in many small intervals. It is having three basic assumptions, like firstly we assume that any time patients who are censored have the same survival prospects as those who continue to be followed. Secondly, we assume that the survival probabilities are same for subject recruited earlier and later in the study, and third, the event have equal time follow up for specifications. This create problem in some conditions when the event would be detected at a regular examination. All we know is that the event happened between two examinations. Estimated survival can be more accurately calculated by carrying out followed step that we are going to see. In this module, we will illustrate the hazard rate estimation using R, the survival curves and hazard rate functions curves using R, and the statistical inference using R.
We are going for Kaplan Meier estimator module 2. Here at the end of this module we will learn how to generate hazard estimate using R, plot hazard rate in R, and statistical inference about hazard rate. Let's start this data taken from metronomic chemotherapeutic trial published by Patel et al. In 2015 on Journal of Oral Oncology. The partial data set is considered here, where arm denoted as 0 for cetuximab arm and 1 for methotrexate arm. Time variable is considered as survival or censoring time. Status is represented to at the end of the follow up what is the status of the patient, as censored or not censored. So ES is represented by 1 for status of the patient, and fourth variable gender of the patient is considered as male or female as a sex, and fifth variable is age. So what the baseline age of those patient is considered here. Now let's see the data. Here first arm, for here few patients partial data set is considered here. For first patients treated with cetuximab arm, that's why it's given as 0. Second patient with methotrexate arm given as 1, like all patients. And if you go to again end part, so you will see the last patient was treated again with the cetuximab arm. So as patients were treated in which treatment given as code 1 and 0. Second variable time considered as days of observations. Since these patients were head and neck cancer patients and they were in having phase 4, so duration of life is expected very less, maybe 2 to 3 months. Here we have seen some patients having days of observations 63, 68, 62 like, and maximum observation here we have observed that 193 days and minimum 19 days. So this time is basically the follow-up observation of each patient. Now coming to third variable, that is status, again given as 1 or 2. So if the patient's censored, then it is given as 1, otherwise it given as 2. So those patient died is given as 2 here. Now coming to the variable sex, it's given as 1 for male and 2 for female. Now coming to age of the patient, that is considered at the study initiation. When they entered in the study, at that time their age is considered, and age is considered at year, like 25 years, 32, 42, 23. Now all these 5 variables is considered into a database called data.frame and assigned as a chemo database. Now if you put the summary of chemo, then you will get the summary statistic, descriptive statistics about these 5 variables. You may try it. Now we go to second slide. Now load the library survival, and here the few work we will do in library survival, and thereafter another library is required, that is called library MuHas. So there are some functions to get the hazard rate that is available in MuHas, but in addition to MuHas we also have to upload on the package called survival, because few function in MuHas is compatible with survival library. Come to next slide. Get a hazard estimate. So now when we upload it in our survival and MuHas package, then we are going for function called kphas.fit, that is available in the MuHas package. When we put kphas.fit and into parenthesis we put the time and status, then and assign the whole function's value as kpfit, then and if we call the kpfit, then we will get the result. That result I am showing to next slide. Again, if we put another function that is called kphas.plot, and into parenthesis if we put kpfit, we will get the plotting variable plotting the survival values here. Now we go into next slide to show the statistics and plot. Here the output given on for this kp has.fit function. You can see that through x-axis the duration of the patients observed in days are given, that is given by time, and through y-axis the hazard rate plotted. Here you can see that maximum hazard rate observed during this period is 0.5. However, this is not the cumulative hazard, this is simple hazard plotting, where throughout the duration of the study how hazard rate keep on changes. We can see that during 7 to 80 days patients are having higher hazard rate, more than 15%, that given through a y-axis as 0.15, and thereafter rate reduce. Again another peak of hazard rate observed during 120 days, nearly 0.7 or 0.8 hazard rate, and again it decrease. So this is the hazard rate, this is the beauty of this function kphas.fit, to plot the hazard rate changes during the study period. It gives some idea what is the chances of the patient having died in which period, and if they complete that period, again what is the chances of their relapse or getting died. So it's a very informative graph to get the idea about the survival analysis, survival comparison. However, in this graph we are not comparing two arms. To compare the two arms there are others method that we will check later, but here this is the respective of the arm. Here we consider all patient data and check how the graphs, how their hazard changes over the period. Now we will come to next function, that is called MuHas. This function is available that we mentioned in library called MuHas. It estimates the hazard function from right sensor data using column based methods. Option include 3 types of bandwidth function, 3 types of boundary correction, and 4 shapes for the kernel function. Uses the global and local bandwidth selection algorithm and the boundary kernel function described in the Muller and Ward 1994 published article. It's also possible to get the nearest neighbor bandwidth formulation based on Kaplan and date 1992 publication. The statistical properties of these Mohs functions are given for many estimator and reported in paper of his in 1999. These estimates are similar in concept of the histogram estimator for the density function. It gives a feel for the feature of the data without manipulation involved in the smoothing. It also helps to confirm that Mohs is generating realistic estimate of the underlying hazard function. It's called, and we will see here that how the plot of Mohs shows. This is the estimates given by the Mohs. So again here the follow-up time is given through the x-axis and hazard rate given at the y-axis. Here how the hazard rate changes throughout the survival time that given by the Mohs functions. And again this is a estimates. Here we are not giving the any confidence interval, only the kernel based estimate is given here for Mohs function. You can see that initially the hazard rate was nearly 0, that's why the survival rate was 100%. As time passes, the hazard rate keep on increase, and end of the study it reached to maximum of more than 4%. So this is a one kind of cumulative hazard rate and alternative of the Kaplan Meier curves. As Kaplan Meier curves as follow-up times increases, Kaplan Meier curves keep on decreases. Here as follow-up time increases, hazard rate function values also keep on increases as alternative of the Kaplan Meier's value. Now we are coming to another function that is called p-has, that also available in the library called Mohs. It also gives the plot. If we give the function p-has and after that follow-up times and follow-up status, or if we give the time and status of the values within parenthesis and assign it as a variable. Here we had assigned it as a feed, and again we call that feed within the parenthesis of plot. Then we get the fit estimates of produced by p-has. Let's see how the estimates looks. This is the R estimates. It gives the estimates piecewise exponential hazard function from the right sensor data. It divides the time domain into bins of equal width and then estimate the hazard in each bin as the number of events in that bin divided by the total follow-up time in that bin. So it's a basically bin wise estimates of the hazard functions. Again here time given through x-axis and hazard rate given as y-axis and follow-ups detailed here. Now we will come to the next presentation, next function, that is library. Now we'll plus 7. Now we will come to another library that is called BS hazard. Basically it's stand for baseline hazard estimations. Again BS into the BS hazard, if we put the function called SURV that is available in the library called survival, and in sub if we put the time and status, here we are putting status equals to 2 for these censored observations, for the date observations, and followed to the data called chemo, and again these BS hazard functions values assigned to a to fit, and again we are calling the fit and plotting the fleet value with time and hazard, and as a x-axis we are putting its labeling as time, and as a y-axis we are labeling at as rate or percentage, and type is basically is used to give the idea about the what kind of line will be there. So in our package, in our CRAN, you may get different kind of combinations or choice for to represent the type. Here we are putting type equals to 1 to get the default line type to represent. Here we are coming to the R output. Let's say how it looks. It looks like that. Hazard rate per person in days given, and again it's quite similar, looks similar in like earlier functions, earlier output, but like given by Pihas, but here it's a wonderful wonderful interpretation can be there, that rate per person per day is given by this BS hazard library functions, BS hazard function also, and again y axis given the hazard percentage and x axis given the durations of follow up. Now coming to generate the confidence interval of that hazard, here we are putting that feeds of raw data, and again as time, and feeds of raw data of hazard, and again CX, LOID and color standing to generate different kind of coloring and line space and type for their plotting. And again if we put that fit lines, if you see the second line is given as line of fit of time and fit of hazard with LTY1, LWT3, that will give us the point estimates value of hazard function throughout the follow-up periods. Second line, lines fit times fit lower dot ci will give us the plotting value for lower confidence interval of hazard function, and lines fit time fit upper dot ci will give us the upper confidence interval value, estimates value of the hazard functions. Now this L2I and LW2 you can changes to get different types of graphs, different color, different width of plotting values, lines in the graphs, but here we are putting L2I equal to 1 and LWD for 3 to represent the confidence interval separately from the point estimates value of hazard. We are putting LWD 1 for lower confidence and upper confidence interval, and LWD3 for point estimates. Now let's see the how looks graphs. This is the graphs. So there is a broader line there. It shows the point estimate of hazard rates at rate per person days given by this earlier function in BS hazard, and again the upper confidence interval and lower confidence interval is given. You can see that point estimate of hazard started from 0 and it reached nearly 0.09 at the end of the study, that is around 25 to 250 day plus. And again the upper confidence interval also started nearly 0.004 and reached again it to more than 0.01 at the end of the study, and again confidence interval lower also started exactly from 0 at the duration of 60 days around, and it reached to nearly 0.01 at the end of the follow-up study. This is the interpretation and the function to generate the hazard functions.
In this module, we have seen the application of R on survival analysis. This module was focused on hazard rate estimation. The hazard rate is a point estimate, gives the how one arm having hazard in comparison to another arm. In null hypothesis, it is assumed that both arms are having equal hazard rate, that is hazard ratio will be equal to 1. The point estimate of hazard ratio if comes more than 1 with its confidence interval also more than 1 intervals, then it can infer that one arm with reference to other arms having more hazard ratio. It depends which arms are considered as reference arm and which arm is considered as intervention arm. Generally, the control groups is considered as reference arm and the interventions or new experiment groups considered as to obtain the hazard ratio. These applications of R to plotting the hazard rate also we have seen in this module. The statistical inference, how to make interpretations from the hazard rate estimations and graphical explorations of hazard rate, we have also learned from this module.